In this lecture, we're going to continue our discussion of some fundamental physics as they relate to absorption spectroscopy to kind of deepen or enhance our understanding of NMR spectroscopy once we get into that topic in more detail. So let's just kind of start with a brief recap. So, whoops, the wrong thing selected here. So for all waves, the frequency and wavelength, frequency is labeled nu and wavelength is labeled with a lambda, are inversely related or inversely proportional. We saw that last time. We looked at two examples, waves A and B, if you recall. So what we can do is we can relate lambda, which is the wavelength, and nu, which is the frequency, using the speed of light in a vacuum, which is c. Well, let's see how we're going to do this before we just start throwing formulae around that we need to memorize. What we first want to recognize is that if we have a speed of light, speed is equivalent to the amount of distance that one or something travels per some duration of time, distance over time. Well, distance, this is the unit of lambda, because wavelength, it's some sort of length. I didn't prescribe a particular unit to us last time, but we could if we needed to. Versus time, well, time is related to frequency, but frequency in particular is 1 over time. Hertz equals 1 over second. So what we could do is recognize that if we take the lambda, which is a distance, times nu, now you might think, well, shouldn't we divide nu? But recall that nu has the unit of 1 over time. So multiplying those two together would give us distance times 1 over time, or distance per unit of time, which we said was a speed. Now, in particular, for any photon, if you take its frequency and multiply it by its wavelength, you will get a common speed, assuming that we're propagating within a vacuum, of c, which is the speed of light. So this speed of light, c, is a constant that allows us to relate lambda and nu together. That is, this allows us, this is one of those things we should know, so I'll highlight it. I mean, everything I say is something we should know, but you get it. This is definitely an important thing to keep at our fingertips. So c equals lambda times nu allows us to determine an unknown lambda or nu if the opposite variable is known, because c is constant. That is, we could, turning the page, nu is equal to c over lambda. Conversely, lambda is equal to c over nu. And while we typically have frequency in hertz or per seconds, the units for wavelength vary, whatever's kind of convenient to use, but you would just change the number for the speed of light by just altering the units, doing a little bit of a unit conversion. You could solve this for any frequency or lambda that's provided. Now, what this is a very useful formula. Don't get me wrong, definitely highly important. But what tends to be pretty useful in this course is to relate, can we relate nu and lambda to a photon's energy? Now, why am I introducing the idea of energy? But if you remember from a couple of lectures ago, we were talking about how photons, while they're all massless and they're all moving at the speed of light, they can be different. Photons can be different in other ways, namely their energies. Okay, so different photons differ in their energies. Different photons have different energies. Now what we can do is we can use another equation that takes advantage of the previous equation I had up in our notes, and that's the de Broglie, probably did not pronounce that correctly, I'm doing my best. The de Broglie equation allows us to determine the energy of a photon from either, so we have de Broglie equation, but another important word there is either the wavelength lambda or the frequency nu. That is, the equation I like to remember is that E equals H times nu. Okay, so I've introduced yet another new word. I realize in my notes I don't have the units for this other word, so I'm just looking those up really quick. But what we could do is E equals H nu. Let's define these terms. So E is our energy. This is what we're looking for, looking to solve. Nu is the frequency of the photon. Now, H is another constant. Okay, so that means it's an unchanging number. It's just a number we have to plug in to get this to work. And like the speed of light, it actually is quite useful in that it's constant for all photons. So this is a particular constant called Planck's constant. Planck's constant, and the number is definitely something that you can look up. As I say that, I'm looking it up. But I remember it's 6.626. I couldn't remember the units. The units are joules times second. So that's the, I believe that's the SI unit. Okay. So joules times second, if you multiply a joules times second term by a frequency of a photon, which is generally in hertz or 1/2, you're going to cancel the seconds and get a unit of energy, joules. Okay, so this is the de Broglie equation. Now, what I like about this equation is, and the reason why I use this is you recall that whenever, if you might recall, whenever in organic one, we wanted to use light as a sort of agent within a reaction, I would always put H nu over the arrow. And that was me taking Planck's constant times a frequency of light. And what I was saying was we need photons of a particular energy to influence this reaction in a productive way. Okay, so that's why I like this form of the equation. But I said that we can figure out the energy using this equation for a photon if we have either, remember I highlighted that word either in our notes, the frequency or lambda. And I'm gonna, or nu, lambda or nu. Put this up here because it's kind of confusing in the notes otherwise. Okay, so alternatively, we could have E in terms of the wavelength of light by just recalling that if c is equal to lambda times nu, then nu is equal to c over lambda. So what we can do is we can substitute that into our de Broglie equation to get us the energy equation with the wavelength. We just have to include then the speed of light. It's got a few more variables, and h nu is what I tend to hold on to a little bit easier. Okay, so what I'm going to do is I'm going to change the page, turn the page. I'm going to say that E equals h times nu, which is equal to h times the speed of light divided by lambda. Okay, so we have these two forms of the de Broglie equation to understand the energy. Now, we need to know what happens when the energy, when the energy goes up or down. This is what we need to know, and this is why this equation is very useful. You might say to yourself, this is already a lot more math than we had to do in Organic Chemistry 1 during the lecture, not the lab component, but during the lecture component. I would totally agree. But what's kind of interesting about all of this is in a typical semester, not during a pandemic, when we have in-class exams where I still have my no calculator rule, we actually don't do calculations involving these equations. But what I want us to recognize is how things correlate. That is, I want to know what happens when the energy of a photon increases or decreases. When the energy of a photon increases, recall this is the energy of a photon, different photons can have different energies. So that means photon energy could go up or down, right? Okay. When the energy of a photon increases, what happens to those two properties of waves, of the photon waves that we were looking at? That is, what happens to the frequency and the wavelength? Well, according to these equations, when the energy increases, the frequency must also increase. And if the energy decreases, the frequency must also decrease. So frequency is directly proportional to the energy. Whereas the wavelength goes in the opposite direction. Now here I'm looking at, I'm just going to temporarily highlight this. Here I'm looking at this equation, okay? That is to say, if the energy goes up and h and c are constant, the frequency, which is now in a denominator spot, must go down for that energy to actually go up. So if the energy of the photon goes down, excuse me, I misspoke. When the energy goes up, the frequency goes up. I already said that, but the wavelength must go down. Now, conversely, if the energy goes down of that photon and its frequency goes down, the wavelength must go up. So I'm using these equations to show what happens to both frequency and wavelength when the energy changes. Now, it's just really good knowledge to have just in all of science to know that frequency is directly proportional to energy. As the frequency goes up, the energy also goes up. High frequency, high energy. Additionally, wavelength is inversely proportional to energy. Okay, so the wavelength is inversely proportional. So what this means is if you're getting bombarded by high energy photons, they have really tiny wavelength and a really high frequency. Okay, we're going to see a lot more periods per second. But if you're going to get attacked by a photon and it's got the longest wavelength ever, you're barely going to feel it. These long wavelength, low frequency waves are very low in energy. Okay, so if we wanted to build a mental map, I suppose, of what this looks like. If we had a high frequency and therefore small wavelength wave, that would be like on the order of a gamma, a wave representing gamma radiation. That's just an example. This isn't drawn to scale, but if we wanted to compare that gamma radiation to a radio wave, we would say this one would be low energy, as an example, a radio wave, which we mentioned previously. Okay, so that's kind of how energy is related to those parameters for a wave, frequency and wavelength. Now let's bring this back to spectroscopy and start warming up for some ideas related to spectroscopy. And to do that, we have to understand something called absorption. And I suppose, you know what, I'm going to take a second. This might be a good break for another video. So forgive me, I'm going to just cut this and make this into a separate video.